SHM and the wave motion topic. First, let us consider one example. Suppose there is a horizontal smooth surface and there is some spring connected. And there is some mass M. It is some mass M. There is a spring connected with this mass. The other end of the spring is fixed at a rigid support. And this entire thing is placed on a horizontal smooth surface. Okay? Now, we consider initially the spring is at its natural length. At its natural length. That means no force is acting, net force is acting on the mass. Because spring is at its natural length, so there will be no elastic force given by the spring to the mass. You are not pulling it. The gravitational force downward and the normal reaction upward will also balance each other. So the net force on the mass will be zero in this situation. Now, we consider that by applying certain amount of force, we will pull this mass to that side. Okay, fine. So you are applying some force and as a result, this mass will come up to this. Then what will happen to the spring? Spring will elongate. Spring will elongate from. So extension of the spring is up to this. So let us consider this is the movement of the mass by an amount x due to your applied force. You are applying some force to pull this mass. So that's why the spring will elongate. Now as soon as the spring will elongate, due to elastic property of the spring will try to come back to its original length. So this force is trying to restore the spring to its natural length. So this force is called restoring force or the elastic force. Clear? So what will be the direction of that restoring force? Opposite to the elongation. So in this case, this restoring force will act on the mass along this direction. So it will try to decrease the displacement always. You pull the mass to one side and the spring is stretched. The stretched spring due to elastic property will try to bring this mass to its previous position such that the spring will be in its natural length again. So this force exerted by the spring is the elastic force. Since it tried to restore the mass to its previous position, it is also called the restoring force. Clear? Now, what will be the magnitude of this force? It is directly proportional to the elongation of the spring. So instead of elongation, if it is compression, then it is also proportional to the compression. So I can write F proportional to X. F proportional to X. So as the elongation increases or the compression increases, this force will also increase. Okay, so we consider F proportional to X. Now, A proportional to X was first discovered by Robert Hooke, and that's why this is called the Hooke's law. F proportional to X, this is also called Hooke's law. Now, from this we can write one constant F equal to Kx, where there is a customary to put this minus sign. Minus sign is to remind you that this elastic force and the elongation of the spring are always opposite. That this displacement and the force are always oppositely directed. Instead of elongation, if you exert a compressive force, it will compress. In that case, displacement is along this direction and it will try to regain its shape. So apply the elastic force in this direction. So in that case also X and F are oppositely directed. So in all the cases, restoring force is opposite to displacement. Clear? Restoring force is always opposite to displacement. That's why it is named as restoring force. And this comes due to the elastic property. Okay. Now, this motion has some similarity. We are particularly interested here in the motion of the mass, not the elastic property of the spring. So for the mass, if you observe, you will find that there is some displacement of the mass along the positive x direction, and there is some force acting on the mass in the negative x direction, trying to decrease the displacement to its zero position. Okay. Now, think about this situation and we will discuss this more. Now, let us consider the mass is here. Suppose at the origin, we consider that this position is at x equal to 0. X equal to 0. So, when the mass is at x equal to 0, what will be the force on it? Restoring force 0. When the mass is displaced to a value, its force is kx, but directed opposite. Now, due to this force, if the mass comes back to this position 0, then what will be the net force at this position when it will come back? Again 0. Force on it again 0, but its velocity is not, because the mass is going in this direction. Mass is going in this direction and force is continuously increasing in the opposite direction. So one time will come when the mass will stop, and then due to this force it will go back to the natural length. Then it will come to this position, but at this moment velocity is actually maximum, so it cannot stop here. What it will do, it will move in this direction, and as a result it will start to compress the spring. Once the spring will compress, it will again develop restoring force, and this restoring force will try to bring the mass back to its x equal to 0, that means natural length again. So it will compress, there is a maximum compression, and then the mass will again stop. Then the mass, due to this restoring force, is going again to this position. Then the mass cannot stop here because velocity is again maximum, so it will go in this direction, and this motion is going forever. That's why it is called simple harmonic motion. This motion will never stop. This motion will continue because you are not considering any kind of friction to the surface. We are considering the surface to be frictionless. So mechanical energy cannot dissipate from the system. It can only convert between potential energy and kinetic energy. So at this position, it has the, when it comes, it has the maximum velocity. So potential energy will be 0, means elastic potential energy will be 0. Kinetic energy will be the total mechanical energy. And when it reaches to the end point, it is momentarily stopped. So kinetic energy becomes 0, entire energy becomes elastic potential energy. Okay? Elastic potential energy. So this motion, in this motion, kinetic energy, mechanical energy is converted between kinetic energy and potential energy continuously, and that's why this motion occurs. Is it clear? Now, here we consider when it is displaced up to a distance x, the force on this is F. Now we consider that there can be a maximum value of x, otherwise it will overtake the elastic limit. So you have to be within the elastic limit for this experiment. Elastic limit means if you elongate a spring, suppose you elongate it this much, it will never come back to the initial position again because it is permanently deformed. So permanent deformation is beyond elastic limit. So the elastic limit is that part of stretching you can do such that when you will release, it will again come back to the same position or same length. Now we consider that the maximum amount of stretching that I can provide to this mass is up to here. So this maximum displacement is written as capital A. So that is called the X max. Which is considered as the amplitude of the SHM. Maximum displacement on either side of the equilibrium position is called the amplitude of SHM. Okay. Maximum displacement on either side of the equilibrium. Equilibrium is where the force is 0. That is x equal to 0 considered here. So on either side, the maximum amount of displacement that you can give to this mass such that it will come back to the natural length again. Spring will come back to the natural length again. That is called the amplitude of SHM. Now, so if it can move up to x equal to capital A on the right side, how much it can move on the left side? X equal to minus A, because it is x equal to 0, it can move maximum up to plus A. Then on the other side it can move maximum up to minus A. So we will consider also that it can move maximum up to x, that is called the x mean, equal to minus A. So this is the 0 value, that is the equilibrium position where net force should be 0. This is the maximum displacement on the positive direction, that is considered as plus A. It is the maximum displacement in negative side, that is considered as the minimum value of x, that is minus. Now, this motion will be SHM if the displacement from the equilibrium is very small. Otherwise, it is not an SHM. It may be a oscillatory motion, but it is not an SHM. Okay. It may be oscillatory, but it may be oscillatory, periodic, all the properties can be assigned, but it will not be SHM. SHM means this property should be maintained. F should be proportional to x. If it happens that F proportional to some x to the power 2 or 3, then it is not an SHM. Because practically when we try to solve the problem, there is the air resistance. Air resistance means the viscosity of air acting on this body. So if you put a large displacement, then velocity will be automatically higher when it is coming back. And as the velocity increases, viscous force will also increase. So that other type of dissipating force will come and it will no more be an SHM. So for the SHM, it is directly proportional to x only, and all this type of friction force, dissipating forces has to be eliminated from the system. That's why here from the beginning I consider the surface is smooth and viscosity and all these forces are neglected. Now, why the motion of SHM is so important? Because most of the time we encounter almost SHM like motion in our nature. Suppose molecular vibration, that is almost an SHM, almost, not exactly, but it is almost an SHM. So any kind of oscillatory motion or any kind of periodic motion can be treated as a sum of many SHMs. There is any motion, any periodic motion, it may not be SHM, but you can consider that it is a large number of collection of SHMs summed together. Then they will produce this complicated motion. So that's why the basic of the SHM has to be learned. Now, what we have to find in this case? Just focus on Newton's law. Newton's law says F equal to m. I consider only the one dimension and don't put the vector sign because this mass motion is only restricted to the x-axis. F equal to ma. What is the main aim of F equal to ma? Provided force is given as a function, mathematical function, it is given, and you are expected to calculate velocity and position of the particle under this force at any time. Means you have a relation where x is a function of time or v is a function of time. Velocity and position of the particle is to be determined as a function of time. That is the main aim of Newton's second law of motion. So we can solve this one. This is a differential equation and find. But now, in general, this F equal to ma, I can write ma equal to minus kx. You know that a can be written as a equal to minus k by m into x. Then this a can be written as minus omega square x, where k by m is considered as omega square. So what we consider here, omega square equal to k by m. And then this x can be written as a can be written as d2x dt2 because acceleration is double derivative of position. So a can be written as d2x dt2. Then take this term on this side and write omega square x equal to 0. This is called the differential equation of SHM. This is the differential equation of why k by m is particularly taken as omega square. Why not omega? Can I take k by m as omega? Why not? Dimension will not match. And why particularly omega? Because you know that k by m, root over of k by m will come in the form of rate, angular velocity. But without solving, how can you say that there is some angular velocity related to this motion? There is no angular motion for this mass. This mass is moving perfectly on a horizontal line. Its motion is a straight line motion. So how can you associate some angular velocity concept with this? Because if there is no angular motion, how can we talk about angular velocity? It is a straight line motion purely. Then for k by m, I can consider any constant. It may be omega only. Not necessarily omega to be angular velocity. You cannot say when I am taking k by m equal to omega square. If you don't know the entire thing, you cannot say that it is angular velocity. It may be some constant c or anything I can write. But how you know this one? That this k by m will become angular velocity square. See, if you proceed mathematically from this differential equation, you have to consider this is some constant. You can consider the constant as omega. You can consider the constant as omega square, omega cube, or anything. That doesn't matter. But from a physical perspective, if we look into this motion, then we can reveal why root over of k by m is related to the angular velocity and what is the significance of angular velocity for this SHM? Because this motion is normally looking, this motion is just a straight line motion. No question of angular motion, so no angular velocity is related to this motion. Now, see, you can solve this differential equation to find the answer. That is entirely a mathematical procedure, and we will not go into that mathematical procedure of solving this second order differential equation. Rather, we will try to emphasize to the problem physically, from another physical approach. See, just below this point, the equilibrium point, I consider this axis. This one is x-axis. Okay. Now, what is the maximum displacement on either side? A. So from this point, taking radius A, draw a circle. So this is the position A. Suppose A, complete one circle. It may be almost like this. Okay? Just complete one circle whose radius is A. Now, just consider this arbitrary position of the mass where displacement is x. Let this point be denoted as P. And from this point, drop a perpendicular on this x-axis. Remember, your x-axis is parallel to this axis, horizontal surface. Your x-axis is parallel to horizontal surface and y-axis is perpendicular. Now, this position, this arbitrary position of this mass is considered as point P, where the displacement from the equilibrium is x. From that point, drop a perpendicular on the x-axis. Now, this perpendicular will intersect the circle at this point. So let this point be denoted by Q. Let this point be denoted by Q. Now check. Join this point. So what is the radius of this circle? A. So this length should be A. Because I am drawing this circle by taking the maximum displacement as the radius. So A radius circle is formed. This point is Q. Now check. I claim one thing, that PQ, this straight line, is always perpendicular to the x-axis. Always. Now look to the motion of particle P and particle Q. What we have done from this position, we pull this particle mass on this side and then released up to A. Then this mass will move. This mass will move and this is performing SHM. So point P is always performing an SHM over the surface. Right? Now, just take. I put my one hand at the position of point P at the extreme end. And I put the other hand at the position of point Q when point P at the extreme end. Where is the position? Here. Now check. If you now released, it will come here, then it is going here, then again. So what happens to the motion of the point P and Q? The time in which point P completes one oscillation, the same time Q takes to complete one revolution. So So point particles point P's motion and Q's motion are not independent of each other, they are dependent on each other. Again see, point P is here, at that moment Q will be here. So these two points should be always vertical. It will come here, then go here to this extreme, again. Okay. So the time in which P completes one oscillation, in the same time Q completes one revolution around the circle. So write down the time, complete the diagram and then write down time it is calculated, and see how the omega comes. For every SHM you can construct a circle. From that circle, the particle moving on that circle has an angular velocity omega. That is coming as the angular frequency of the SHM omega. That is the relationship. So if you observe only the linear SHM, you cannot find what is omega, because linear motion there is no concept of angular speed. But if you see the corresponding reference circle, then you can understand why the omega will come for the SHM, because it is actually related to the oscillation of rotation of that particle Q, which is over a circle. Okay. Now, so at t equal to 0, the particle is here, at x equal to a, just put t equal to 0, you will get cos 0 will be 1, so x will be equal to a, so the motion starts from here. It may happen that the observer observed not from the one side, it may observe when the particle is here or here, any arbitrary position. That's why some arbitrary phase has to be included. That's why the general equation is written in this term with some phi. This phi remind you that particle may start, observer may start to observe the motion from this point. This additional angle is taken as phi. So this is similar to the concept when you solve the kinematics problem. All the time is it mentioned that the particles start from rest? Initial velocity is 0. No. Sometimes you got initial velocity to be 10 meter per second. Means the starting point is, you are not observed starting point. The observer starts his observation when the particle has a velocity of 10 meter per second. Then he considered this one as the initial velocity. So the same thing. Observer may not start from this point. It may start from this point, and as a result there should be some initial phase angle. So this phase angle is denoted by phi. So this is the equation of an SHM. Now as well, since this is a cosine function, so it has another counterpart as sine function. So you can also represent this SHM equation by a sine omega t plus phi, or any combination of sine omega t and cos omega t. It can be written as a sine omega t plus b sine omega t, b cos omega t. This combination is also possible for SHM, because all these combinations can be converted into this type of form. Okay. So this is the equation of an SHM. You can write, I write here with cos, you can also write here with sine. Fine. So no need to solve the differential equation. From this reference circle we can find this one. Now, why omega square equal to k by m? That I haven't discussed. Here I completely consider a different motion, which is a circular motion, which has some analogy with the original SHM, because the particle Q and particle P always have the same x coordinate. Clear? Now, if this x coordinate is also the x coordinate of particle P, then if I put this value of x in this differential equation, then it will be satisfied. Because if you find some solution of a equation, say a quadratic equation, x square minus 3x plus 2 equal to 0. After solving, if you get x, you will get two values, x equal to 1 and 2. And then if you put 1 or 2, any value in this expression, left side, you will get 0. Just check, if you put 1 square, that is 1 minus 3 plus 2, it will be 0. If you put 2, it will become 0. So after solution, after getting the roots, if you put the roots in the equation, it will be satisfied. The same thing, I am claiming that this x, this value of x, this expression for x is the solution for this motion. So this motion has a differential equation, this one. If I substitute this value of x here after differentiating 2 times, then it will be satisfied. So just differentiate it 2 times and substitute here. Then you can get omega square equal to k by a. Check. I want to differentiate it, dx dt. How to differentiate this one? This is a. Cosine function will be minus sine omega t plus phi. Now there is omega t plus phi, so due to chain rule we have to differentiate again. So this differentiation will give you omega, and phi is a constant, so its differentiation will be 0. So another omega will come out. So it will be minus omega a sine omega t plus phi. So we have to take the double differentiation because there is d2x dt2. So I want to differentiate it once more. d2x dt2. And what it gives? It will be minus omega a will be there. This one will be cos omega t plus phi. And due to chain rule, another omega will come out. So it will be omega square. Okay. It will be omega square. So this is the acceleration. Right? Now a cos omega t plus phi, what is it? X. So you can write it as minus omega square x. See, this differential equation is satisfied. d2x dt2 equal to minus omega square x. That same thing is coming. So omega square should be k by m, that we can already argue. So from this actually we are arguing that omega square equal to k by m. Because before this step, when you write this one, if you are not taking this one as k by m, you will just write this one d2x dt2 equal to minus k by m into x. And if both of these acceleration are same for the particle p, then this side should be equal for both of this equation, because left side is d2x dt2. So I can equate them. Equating them, what we can write? Minus omega square equal to x equal to minus k by m. So x cancel. So what we will get? Omega square equal to k by m. So now we get that omega is not k by m. It is omega square, that is equal to k by m. So this is the differential equation in the format of k by m. Now we are getting this one. Both have the acceleration of the same particle. So this should be equal. So if you equate the right side of this equation already, because left side is already d2x dt2, So minus omega square x will come out minus k by m into x. Then x cancelled, minus minus cancelled. So omega square will become k by m. So that's why omega square is taken as k by m. Okay? Achha, can I erase this portion? See. Now from this we can write many things. Omega square is then root over of k by m. Then omega can be written as 2 pi by t. So 2 pi by t equal to root over of k by m, or time period of oscillation is 2 pi root m by k. 2 pi root m by k. This is for the spring. 2 pi root m by k. Where k is the force constant of the spring, or spring constant, and m is the mass that is oscillating. Okay? I think one type of problem in your paper 4, 5 or paper 4, there is a question related to this formula. The time period is required for the spring calculation. The mass is changed. Mass is previously something, now 1 kg mass is increased. 2 time periods are given, then you have to find the amount of original mass. Okay? Now, we can calculate some other formulas related to general SHA from these calculations also. We are taking a particular case, but since it is a SHA, this one is a particular case of spring, having spring and mass system, but that calculation is a general calculation in terms of omega, and from that we can derive some general formula for velocity and etc. energy of the SHA. See, first of all, in this calculation, this term is the velocity of the particles executing SHA. dHdt makes instantaneous velocity. So write it V. So V can be written as minus omega A sine omega t plus phi. Right? Minus omega A sine omega t plus phi. Now take a square on both sides. So it will be V square equal to omega square A square. This term will be sine square omega t plus phi. Sine square omega t plus phi. Right. Then we can also write this is equal to V square equal to omega square A square. Now can I write this one as 1 minus cos square omega t plus phi. Sin square theta can be written as 1 minus cos square theta. So we can write this one. Sin square omega t plus phi equal to 1 minus cos square omega t plus phi. Then V square equal to, first term is omega square A square minus, what will be the second term? Omega square A square cos square omega t plus phi. But apart from omega square, what is A square cos square omega t plus phi? Multiply this term with 1 and then this term with this one. So if I, on the second term, I take omega square separately and then a square omega cos square omega t plus 5, that is nothing but x square. This x square, a square cos square omega t. So write it x square. This can be written as directly x square. Okay. Now, then v square can be written as taking omega square common, a square minus x square, and accordingly you can write v equal to omega into root over of a square minus x square. But don't forget to put plus minus. Okay. Now, what is the significance of this plus minus? If you put the x particle is at the extreme end, that is x equal to either plus a or minus a. In both the cases, x square will become a square. If x equal to plus a or x equal to minus a, in both the cases, this x square will become a square. A square minus a square will be 0 and v will be 0. So at the two extreme ends of the motion, velocity will be 0. Okay. Now at the mean position, if you put x equal to 0, then at the mean position you will get omega a. But what is the significance of plus minus? One time it is coming along this side, so its direction is towards the negative x-axis, then it will be minus omega a at the mean position, velocity. And when it is coming back, it will be plus omega. So that's why I put this plus minus. So it can cross the mean position from left side or from right side. Depending on that, the velocity sign will become positive or negative. Clear? Now, after this one, we want to calculate the total mechanical energy of the SHM. Total mechanical energy of the SHM at any moment, at any instant. Okay. See, mechanical energy means kinetic energy, potential energy. Fine. I will erase all this. See, total mechanical energy, suppose E, that is equal to half mv square plus, for the spring, potential energy is half kx square. If the elongation is x, half kx square. This is the total mechanical energy. Then write half m v square. What is v square? Here. Omega square a square sine square omega t plus 5. Put it. Omega square a square sine square omega t plus 5. Half kx square. Write it. Half. What is k? K can be written as m omega square, because omega square equal to k by m. So it will be m omega square. Now x square. What is x? A cos omega t plus 5. So x a square cos square omega t plus 5. Now take half m omega square a square common. Half m omega square a square. That is common, and that is your answer. Because sin square omega t plus phi plus cos square omega t plus phi is 1. So it does not depend on time. If it does not depend on time, then throughout the motion at any time, the total mechanical energy will remain same. So that's why it is maintaining the conservation of mechanical energy. And why it is maintaining the conservation of mechanical energy? Because we haven't considered any dissipating force like friction, viscosity, all these are eliminated. So how the mechanical energy will be converted to the other form? It cannot convert, so it will remain same. And as a result, the oscillation will go on forever. In practical situation, oscillations are not going forever because we cannot completely eliminate the dissipating forces. Because we can decrease the viscous force, but we cannot completely eliminate it. Since it does not depend on time, it will not depend on the total mechanical energy, will not also depend on the position x, because x is a function of time. So at any position of the particle in SHM or at any time, the total mechanical energy of the oscillator will remain same, that is conserved. So like when we discuss work for energy, I said that work for energy is an alternate procedure to Newton's law. Because it is a scalar formulation, it is much more easy than Newton's law to apply. So starting from this conservation of mechanical energy, you can also derive the differential equation of the SHM and Hooke's law. Just the reverse procedure, you have to differentiate this one, this form, because d dt will be 0, then you can differentiate and you will get back Hooke's law and differential equation of the SHM. But that is not required for now. There are many examples of SHM. I will discuss only one. That is most important and coming in the exams, any type of exam, NEET, any other kind of exam, and some questions may arise from that part of that type of motion, which is not even SHM, but in other chapter that type of motion will be discussed. That is the motion of a simple pendulum. Because there is another type of SHM you can normally feel. Suppose a plastic ball, put it over a water surface. Plastic ball will float. If you gently push the plastic ball inside, small amount, and then release, plastic ball will move up and down, and that motion is also an SHM. So there are frequently you will find SHM in the nature. Now we will discuss particularly the pendulum motion, because pendulum related problems will come frequently. Suppose this one is a rigid support and there is an inextensible and massless string, and from this string a pendulum bob is hanged. Pendulum bob, this one, is hanged. Its mass is m. The string is considered to be massless and inextensible, and a pendulum bob is hanged. Okay. Now you are taking this pendulum bob at this position, provided the string at all the position is taut. Means not that you are taking the pendulum bob here and then this pendulum bob will fall and then start to oscillate. In the taut condition, pendulum bob is taken here and then released. So when you will release this bob, it will perform this type of a motion. It is a oscillatory motion, but we have to prove whether it is an SHM or not. Whether it is an SHM or not, and we have to find the time period of that SHM. Clear? Now, first of all, if you consider this type of a motion, this cannot be an SHM. What I draw in this figure, if I truly do this experiment, this will not be an SHM, not even close to an SHM. Why? What figure I have drawn, if I do the experiment with this type of a figure exactly, I will not get an SHM. See, when you pull the mass here and then release, it will move along this direction, and velocity of the masses is not very small such that you can neglect the air friction, that is viscosity. And in presence of viscosity, energy will dissipate in the form of non-mechanical energy, and you will not get SHM, because SHM must obey conservation of energy. Mechanical energy, conservation of mechanical energy must be obeyed in SHM, because if there is resistive force will slow this one, and it will, after some time it will stop, but SHM will never stop. So that means to get an approximation close to SHM, we have to neglect the viscous force. When we can neglect the viscous force? When the velocity of the particle is very small. So that's why this initial angle from where it is released, that should be very small. How much small? It is generally taken as theoretically it should be less than 4 degree. 4 degree. That is, even we cannot release it with an angle of 4 degree. It is so small. Means actually tends to 0 it should be. You have studied the limiting condition in class 11 or 12 calculus. So it should be tends to 0, that angle with the particle. In that case, normally for physical experiment, this experiment is also there in class 11 syllabus.
Lockdown.
Oh, at that time lockdown. Okay. This experiment was there in class 11. Pendulum experiment, and some student and they are taking that you have to measure the time period of oscillation for this experiment. So they are giving a stop clock, and after giving that stop clock, you have to measure this one, and with this stopwatch, some students are advised to take 20 measurement or 25 measurement of time period. Means this is a very boring practical. Actually, you will put the mass here, and when you release this one, immediately you have to start your stopwatch. Okay, then you have to count the oscillations. It is going here, coming back to this point. This is one oscillation. Going here, coming back. 2 oscillation, 3 oscillation, and teachers are saying take almost 30 oscillations to 40 oscillations. 30 oscillations or 40 oscillations you have to count, you cannot miss, and immediately when the 40 oscillations complete, you have to stop the stopwatch. Okay, if you missed, then you have to do it again. The problem is that most of the students say, okay, 40 stopwatch, and you are saying 1 degree, just this much, it will stop before 40 oscillations. Okay, I will start from here and take. What they will get? They will get a value which is which is truly wrong. Suppose actual time period should be 2 seconds, they will get a different value, 4 seconds, 5 seconds, like this. Why? Because first oscillation it comes here, in second oscillation it will come suppose here, then here, because viscous force is too large, and even before 40 oscillations it can stop. So what you are actually frightening that before 40 oscillations it will stop, so that's why I take the large amplitude. That is actually wrong. as small as the angle of deviation you will take, it will oscillate more and more. So even if you take this one, you can take up to 80 oscillations, it will not stop. But if you take large displacement, after 20 or 22 oscillations, it will definitely stop. So that is the problem. Okay, because in that case, viscous force is so strong, it will stop the motion. Now, first thing is this one. Second thing, you cannot take large amplitude. Even if you consider, okay fine, I find a vacuum, complete vacuum, there is no air resistance, how will you challenge? I will start from this angle. Like this. Not in a straight line. And your answer will not match. So now you can say that, okay, fine. I will neglect this effect also, I will do the practical in completely gravity-free space. Pendulum will not oscillate. Because the gravitational force is there due to which pendulum will oscillate. Okay, so you have to remember these things and this angle should be very small. So initially for the drawing, I draw this one at a large angle such that the diagram will not be very hazy or disgusting. See, now at this point, first when you put it here, it may be put it here. So I consider an arbitrary position. This is not the maximum displacement. It can reach, suppose, up to this. Suppose. And this is completely an arbitrary position. And in this arbitrary position, I want to draw the forces first. Clear? What are the forces? One is mg, acting vertically down. One is tension. I write T prime because I reserve T for time period, so that's why I use tension to be T prime. Is there any other force if the motion is considered to be at a very small angle? No other force, because I can eliminate viscosity, Coriolis force, centrifugal, all these things. Now, what is the displacement of this mass at this position? X. Now, for SHM, there should be some restoring force which will bring the mass back to this position. SHM means there is some restoring force which will try to bring the mass back to the equilibrium. Because this is not an equilibrium position, because tension and mg cannot balance each other. But at the equilibrium position, tension and mg will balance each other and net force will be 0. So for that, I want to split these mass forces into components such that it can produce a force which will bring the mass back towards the equilibrium. Okay, to find the restoring force. Now take, which one should I resolve? I can resolve T prime. I can as well resolve mg. Here I will resolve mg by considering one coordinate as of the length, another coordinate perpendicular to the length. Perpendicular to the length, remember. So this is one direction of one component of mg, and that is the other component of mg. Right? This is along the length. This one is one coordinate. This one is another coordinate, and these two coordinates should be perpendicular to each other because we are using rectangular resolution. Now, if this angle is theta, then this angle is also theta. You can say immediately that this component will be mg sin theta. No, mg cos theta. And this component will be mg sin theta. Now check which force, which part of the force is restoring. Mg sin theta. Because T is prime is not the restoring force, because it will not try to move this mass towards the equilibrium. Equilibrium is this one. mg cos theta is also along the length outside, so it is not the restoring force. The only force which will try to restore the mass to its previous position, equilibrium position, that is mg sin theta. So this should be the restoring force. So I write restoring force for this problem, because unless you are getting restoring force, you cannot claim that motion is SHM. Restoring force equal to mg sin theta. Now, in Hooke's law, what you find? Restoring force should be opposite to displacement. Is it opposite to displacement? No, it has some angle with displacement. It is not along the same line. Then how can you write the vector equation that f equal to minus kx? You cannot write. Then we are again in problem. Because for restoring force, if there is displacement x, restoring force should be exactly opposite direction, means their angle between them should be 180 degree. But here it is not 180 degree. Clearly the x is along some direction and mg sin theta is making some angle with it. So they are not along the same line in opposite direction. Clear? So what is the only way? Just draw the path of motion of the particle between 2 points. It is moving along a which type of path? Circular arc. No? It is moving along actually in a circular arc. Then if you decrease this angle, if you consider this angle is very small, then this mg sin theta will be tangent to this path, and this x is also become tangent to this path. If angle theta is very small, if initially x is a secant line, you know secant line? Secant line means, suppose this is a circle, this is a straight line which cuts the circle in 2 points. Now if you take the second line here, so the length of the second line will decrease further. So when 2 points will exactly overlap, then the second line is called a tangent line. So second means which cut the curve at 2 points. When these 2 points will overlap, means the second line will cut the curve only at 1 point, then this is not called secant. This is called tangent to the curve. So now mg sin theta is already tangent, and x will become tangent only when this theta will be very small, means this much small. You cannot differentiate between these two. So both are along the same line in opposite direction. So for that, what should we do? We have to take theta to be very small. So that's why I am arguing, whatever be the factor, even if you completely say that Earth has only gravity, Earth is not rotating, Earth is not revolving, there is no air friction, nothing. Still, if you take large angle, it is not an SHM. Because for the SHM, you have to find out that displacement and restoring force are exactly opposite to each other along the same line. So for this, theta should be very small. If all the restriction I will remove, still theta should be very small to be an SHM, to be a SHM. Fine? Now, then if theta is small, then sin theta can be written as theta, not mg, only theta. Theta is very small, but I am not if you write mg sin theta equal to mg, then theta is actually 90 degree. Sin 90 will be 0, that is very large. Okay, see, you have studied this one in class 11 or 12. This is a theorem of formula of limit. Limit theta tends to 0, sin theta by theta equal to 1, provided theta should be measured in radian. Theta should be measured in radian. So with this logic you can write that if theta is very small, then sin theta, limit theta tends to 0, sin theta is approximately equal to theta. So I can directly write sin theta equal to theta. Provided in radian I can only write. Then this will be a restoring force, and immediately we can write restoring force should be equal to mass into acceleration according to second law. So mass into acceleration will become minus mg theta. Restoring force, then it is minus, and according to Newton's law, the restoring force or any external force will be equal to mass into acceleration, ma. Now consider the length of this wire is L, length of the string is L. Okay, then m cancel, acceleration A equal to minus. Now what about theta? See, if this is theta, this is the L. So this L is here the radius of the path, that is L. And what is the arc length? If theta is very small, this x can be considered as the arc length. Theta is very small because these two lines are now not different. This is almost same. So x and arc length are same. So we can treat x as the arc length, and arc length should be equal to radius into theta. You have studied this one, s equal to r theta. So from this formula I can write here x equal to r theta, but r is here L, so it will become L theta. In trigonometry in class 10, this is the first formula when you are studying the concept of radian. What is 1 radian? So then arc length equal to radius into angle subtended at the center measured in radian. So x should be equal to L theta in this case. Just put in place of theta g x by L. G x by L. Acceleration equal to minus g by L into x. Now, what is the acceleration equation for SHM? For the spring problem we have derived A equal to minus omega square x. Check. Equation of acceleration in SHM. A equal to means d2x dt2 equal to minus omega square x. d2x dt2 means acceleration. So I can write from the general form that A equal to minus omega square x. So this motion is similar to directly proportional to x. So this is an SHM. So pendulum motion when angle is very small, it is similar to the motion of an SHM. Then comparing these two equations, I can write omega square for this problem will be g by. So omega equal to root g by L. So time period t equal to 2 pi by omega, that is 2 pi root L by g. 2 pi by omega. By omega means root g by L is denominator, so it will become root L by g. So that is the time period relation for simple pendulum. Many problems will come from this. T equal to 2 pi root L by g. Suppose length is changed, pendulum is taken under the mines, etc. Then G will vary, and related to that many problem will come. Okay? Cos theta is vanished. Cos theta tends to 1. Theta tends to 0 means 0 to 1. Tan theta tends to 0 means tan theta equals to theta. Theta by 1. Okay, so this one is the simple pendulum. Any question? If you have any question, you can ask. Regarding this, if you have any question, you can ask.
Why is it that when you take theta very small, you don't consider the viscosity of air?
Again, say.
If you take theta,
Huh.
if you take theta is very small,
Huh.
you don't consider the viscosity of air.
Yes, because if theta is very small, then velocity will be very small. And if velocity is very small, then viscous force will be very small, because viscous force is directly proportional to velocity.
So it means both of them
Must not be present, but it should be present, but very minimum. Because actually you cannot eliminate the non-conservative forces completely, but you can minimize it up to a certain limit. Because SHM is an approximation. It is an ideal motion. But if you can solve it, but it can be solved completely. Once you can solve completely, then some viscous force, it is damped harmonic motion, damped vibration. So modifying the SHM equation, I can directly write the damped motion. Okay, so this one is the SHM part. Now based on this SHM part, we will proceed to study the wave motion and all these things. Because there are some other things of SHM that we will not discuss, because other cases of SHM, that different type of motion, you have to consider that this one is an SHM, that one is an SHM, like that. Okay? You can take 5 minutes break and then we will start the wave. See, what is wave? What is wave? Oh, where is this one? is some kind of disturbance produced in a medium. If we talk about the mechanical wave first, then some kind of disturbance is produced in a medium. But in case of non-mechanical waves like light waves, there is no medium, but still there is some disturbance is produced, and that is produced by the oscillating electric field and oscillating magnetic field. Now, in generally, when we talk about the mechanical waves, we can consider that wave is some kind of disturbance that is propagating through a medium. It will carry with it momentum and energy. It will carry with it momentum and energy, means these are the mode of energy and momentum transport from one position of the medium to other position. One position of the medium to one other position, it will carry momentum and energy. These are the same as that of the momentum and energy transport. Suppose I have a stone, okay, and I throw it to any one of you. Okay, so this kinetic energy is traveling with this stone. So this kinetic energy is transported from one portion to another portion. Not only that, it will deliver, I have given it some momentum, because this is a mass, I will throw it with certain velocity, so it has some momentum, and it will carry the momentum up to his body and collide, and transfer the momentum to his body, because it will apply force. Force application means transfer of momentum. So this particle can carry momentum and energy with it and transfer it from some other portions. So particle is one mode of traveling, particle motion is one mode of energy and momentum transportation. Clear? Similarly, wave motion is another mode of transporting energy and momentum from one position to another position. This is a different method from the particle motion, that is called wave motion, but both are actually transporting energy and momentum. Clear? So write down particle motion and wave motion are the two different modes. Particle motion and wave motion are the two different modes of transporting energy and momentum from one position to another position. From one position to another position. Okay? Transporting energy and momentum from one position to another position. Now you can say that, okay sir, fine, but in case of a light wave, it can even pass through vacuum. So how it can transport energy or momentum? Light can transport energy, that is already clear. Because from sun, light is coming to the earth, it is covering a vast distance through vacuum, and after that it will deliver the energy to us in the earth. So that is, energy is already transported. Now how momentum is transported? Light particle is carrying photon, and photon has some momentum that you have studied in modern physics, and that momentum is calculated by E by C, energy by h nu divided by c, that is the momentum. So light is also transporting momentum from one position to another position. Okay. Now, so this is the general case of the general idea about the wave motion. Now we can think about two types of wave on the basis of whether it is requiring medium for its propagation or not. One kind of wave is mechanical wave, which requires a medium for its propagation. That is sound. It is an example of mechanical wave, because in vacuum sound cannot propagate. So mechanical wave requires a medium for propagation. There are certain waves, non-mechanical in nature, which can pass through some medium, or even it can pass without any medium. That is light. Light can pass through vacuum, light can even pass through water or glass, these mediums. So medium is not necessary for their propagation. But through some medium it can propagate, and even through vacuum it can propagate. So these are the two categories of the wave, depending on whether they are requiring medium or not requiring medium. Now, depending on the motion of particles of the medium, we can again distinguish, we can again categorize wave into two categories. One is transverse wave, another is longitudinal wave. So for a common idea of the transverse and longitudinal waves, I consider a mechanical wave. Let us consider a spring. It is, or a string. It is completely stretched between the two supports. Just consider a spring. It is connected between these two supports. Okay, two side wall, it is stretched. Now, you hold one portion of the spring, pull it down, and then release. Actually, you are plucking the string down and then release. What will happen? This portion, due to elasticity, try to move towards the natural position, natural length, but it cannot stop here because of it has some velocity, so it will move up. But again, when it is moving down, up, the restoring force will be in the opposite direction, downward. It will try to move it down, so it will come here. But again the velocity increases, so it cannot stop, it will come here. So actually the particles of the medium are vibrating up and down. Even we can consider in certain case this motion is SHM. So a particle is moving up and down. If you pluck this one and release, the particle is performing SHM, but the wave is propagating along the string. You will feel that entire string something is vibrating and moving in this direction or in this direction. So wave is propagating along the string, particle is vibrating perpendicular to the string. So angle between them is 90 degree. Particle is vibrating up and down, and wave is propagating horizontally. So angle between them is 90 degree. So this type of vibration is called transverse vibration, and the wave propagating through the string is called the transverse wave. Okay, now think about a different situation. You hold one position of the spring, pull it to one side. So this portion spring is compressed and this portion is elongated. Now you release this one. So due to compression there is some elastic force which will try to bring it back to its natural length. So this compressed portion will try to move in this direction. So this portion will become elongated, this portion become compressed. So this is called compression and rarefaction. So this compression and rarefaction pulses will move like this. So particles are vibrating along the horizontal direction. Wave is also propagating along the horizontal direction. So they are along the same line. So this wave is called longitudinal wave, means along the length. So if the particle vibration and the wave propagation are perpendicular, then it is called transverse wave. If the particle vibration and wave propagation are along the same length, same direction, it is, or in opposite direction, means along the same line actually, then it is called transverse. It is called longitudinal wave. Okay. So two categories depending on the particle vibration and wave propagation. One is transverse, another is longitudinal. Now, in case of light, no particle is vibrating when light is coming as in through vacuum as a wave. So then, which one? How we can consider it is transverse wave? Because if the light is propagating along this direction, then in this direction electric field will oscillate, and in this direction magnetic field will oscillate. And this oscillating magnetic field and electric field are both perpendicular to the direction of velocity. So that's why it is also called the transverse wave. Light, transverse wave. But when we talk, so normally when we talk, how the sound will move? Because through my mouth I am producing some pressure on the nearby air column. This then air column is pushed. So this portion is rarefaction. The pushed portion is compression. So this compression and rarefaction pulses will continue to move through air medium until it will reach your ear. And then it will hit the membrane and then you can hear the sound. So that is a longitudinal wave. So sound is a longitudinal example of longitudinal wave and light is an example of transverse wave. Now, suppose there is a calm and quiet water in a lake and you drop one pebble on the water. Then water ripples will form. Which type of wave it is? On the surface of water, water ripples. These are transverse wave. Because if you drop a plastic cork, you will see that the cork will move up and down. And water ripples are moving towards horizontally, moving horizontally. So angle between the particle vibration and wave propagation is perpendicular to each other. So angle between them 90. So this is an example of transverse wave. Okay. Now, we will start from the equation of a wave, and before that I will write two things. I consider transverse wave. This one. Transverse. Now, what do we mean by periodicity?
Repetition of properties after certain interval.
Repetition of properties after certain interval. Achha, what do we mean by interval? Is it only the time gap, or it can be the gap of anything? Gap of anything. It not only the time gap, it may be the gap of a distance. That is also possible. Now, suppose you are considering this transverse wave and someone of you is asked to focus on a particular particle which is vibrating. Say this one, P. You are not allowed to look at any other particle. Only you are looking at particle P for a long time. What you will observe? You will observe that from this top, suppose particle P is at some top position when you start your observation, then it is going down, goes to a bottom position, then again moving up, then again going down, again moving up, again going down, again moving up, and so on. And you will find that to complete one oscillation, it requires a certain time which is constant. Means it starts from P and again going to the bottom and then come back P. Suppose it takes 10 seconds. Then next time you will find again it will go down and come back in 10 seconds. Again go down and come back in 10 seconds. Means you can say that the displacement of the particle repeats its phase, not the value. Because value, magnitude of displacement is here and here are same. But the phase is not same. Because it is in the upward side, it is on the downward side. So displacement of the particle repeats its magnitude and phase after a certain interval of time. It is the phase which is repeated after a certain interval of time. So that's why it is called a periodicity of time and named as time period. Okay, so wave has one periodicity over time, that is called the time period, measured by the quantity time period. Okay, in SHM there is only one type of periodicity because that is time period, but this is a wave, so it has two types of periodicity. So first write down this one. The particle P is repeating its phase. Particle P is repeating its phase after a regular interval of time. After a regular interval of time. Which is called the time period. This is one kind of periodicity. Okay. Now, what you have done here, you focus on a particular particle for a long time. You are not looking what the other particles are doing. Other particles are also doing the same thing if you observe to any some other particle. So for all particle, time period will become T. Now, in this case, we are observing to a one particle, means the position coordinate of that particle along the x-axis is fixed. And time is not fixed. I took the phase of the particle for a long interval of time over and over again and again. So time is freeze, time is not freezed, but the position of the particle is freezed. We are not looking to the other particles. Now we do the opposite thing. Time will be freezed and position of the particle is not freezed. We will look at different position of the particles which have the same phase of displacement. Displacement are in same phase. Okay, see how. So entire string is vibrating. Just take a snapshot of the vibrating string. You will get this type of a picture in the photograph. That means this is the structure of the string at a particular moment. So time is now freezed. And look at different points. This point, this point, this point. So means which coordinate is now changing? X coordinate. The position coordinate is changing and time is now freezed. Because you are taking as photocopy. You are taking a snapshot. So snapshot means it is the impression of the string at a particular moment. So the time is now freezed and you are taking the displacement, the points which have displacement in same phase. And you will find that all such displacement are differing by same distance. So this is a periodicity of position coordinate. After regular distance, the phase of the vibration will repeat itself. Means same value of displacement will come with same phase. Clear? Same value of displacement will come with same phase after a constant distance. Then this constant distance is taken as wavelength. Wavelength means after a distance lambda, the phase of the vibration will be same. Repeats itself. So previously it is after a regular time phase of the vibration repeats. Now after a regular distance phase of the vibration will also repeat. So that is periodicity of position coordinate, which is measured by wavelength. So periodicity of time coordinate is measured by time period. Periodicity of position coordinate is measured by wavelength. Wavelength, periodicity of space coordinate, we can say. It is measured by wavelength. Okay. Then, if it is a simple harmonic wave, means the particles are vibrating in SHM, I can say that the time in which it repeats its phase, in the same time the wave propagates a wavelength. The time in which phase is repeated, in that same time the wave will propagate a wavelength. Means in time capital T, the propagation distance traveled by the wave is lambda. So lambda distance is traveled by the wave in time capital T. So one wavelength is traveled in one time period if it is simple harmonic wave. Okay. Then what is the speed of the wave? Lambda by T. Speed of the wave is then lambda by T, because lambda distance is travelled in capital T time. Now 1 by T can be written as frequency. So you get this formula, V equal to n lambda. Sometimes it can be written as f lambda, nu lambda, anything, because frequency can be denoted by many symbols. So speed of a wave equal to frequency into wavelength. Now we want to write the equation of the wave. Now what do we mean by equation of the wave? This kind of equation you will see y equal to a sine omega t minus kx, or sometimes it can be written as kx minus omega t this time. Kx plus omega t, kx omega t minus k plus kx, this type of equation you will find. Now what is y? What is y? Displacement of which particle or wave? Y is the displacement of particle or displacement of wave? Wave is propagating in horizontal direction. So how it can be the displacement of the wave? It is the displacement of the particle, which we consider the transverse wave for better understanding. It is the displacement of the wave, suppose at this point. This is y. So this particle is vibrating up and down. Its displacement is at any instant of time is taken as y. Okay. Now suppose at t equal to 1 second, how many particles can have displacement y? Many particles. This one, its phase is different. This one, this one, this one. How many of them are in same phase? 1, 2, 3. These 3 are in same phase, because after that it is coming to 0, but here it is increasing. So after that it is a 0, after that it is again 0. So many particles should be there at time t equal to 1 second, which have the same displacement. Then we have to identify the particular particle. That's why another coordinate is involved here. The position coordinate x. Suppose it is at x equal to 5. Suppose it is at x equal to 10. It is at x equal to 50. So which particle's vibration you are denoting and which time, at which time it is denoting. So particle is at some position of x and its vibration is recorded at some time. So the displacement of the particle y is actually depending on 2 factors. One is time, another is location of the particle on the horizontal line. That means y is a function of 2 coordinates. One is x coordinate, another is time coordinate. So that's why y is a function of x and t, and that's why it is wave. Because if you consider x is 0, then it is just SHM for a single particle. There are many particles, because otherwise the medium will not form and it will not be a wave. If you consider single particle, then there will be no wave. If you directly put x equal to 0, then you are looking at the particle which is at this point. So it is no more a wave. It is just a particle vibrating SHM. Now if you add x coordinate also, that means you are looking to every particle at every time. So that constitutes the medium. In that case, you are getting that the particle is due to particles vibration, the disturbance is propagated through the medium, and that is called the wave. Clear? So this is the explanation of this equation, why t and x both are given. Y should be a function of x and t, because if y is a function of only t, then one particle is there and it cannot produce wave. There should be a extended medium for the propagation of the wave. Okay. Now, this one is a equation of plane progressive wave, plane progressive harmonic wave in positive x direction. Because this one is propagating in positive x direction. If this sign is positive, then it is propagating in negative x direction. So write down this one. This equation is a plane progressive, representing plane progressive harmonic wave. Plane progressive harmonic wave in positive x direction. Okay. Now, two things that we can calculate here. One is particle velocity, another is wave velocity, and both are different. First, if you calculate the derivative of the y coordinate with respect to time, you will get the particle velocity, because particle is vibrating in y direction. I consider the transverse wave. So I can write the particle velocity here. Del y, del t. Achha, why I use this del symbol, not t? Because y is not a function of only time, it is also a function of x. So partial derivative has to be done. So when we use this symbol, we are getting the Vp, that is velocity of the particle executing the vibration. And what is the rules for taking this partial derivative? This t is only considered as the variable and x is considered as constant. So its derivative will become a cos omega t minus kx, and from the chain rule, if you calculate the derivative of this part, 1 omega will come out, and kx part is constant because we are differentiating with respect to time. So kx part's derivative will be 0. Okay, since it is partial, then we can consider only x is constant, otherwise it is not constant. So this is the velocity of the particle. See, dx dt that I have to calculate. So I will calculate it later. Meanwhile, I want to calculate one more thing. If I calculate this one, it is not any velocity, del y del x. This is basically the slope of this graph. Just calculate this one from this. It will be a, derivative of this sine function will be cos omega t minus kx, and differentiate this term. Then when you are differentiating x with respect to x partially, then this t part will be constant. So this derivative will be 0 as before. Previously when we are taking del t, then x is considered as the constant. Now we are differentiating with respect to x partially. So t part is constant. So its derivative, it will be minus k x with respect to x, that is 1. So only minus k will come out. So it is coming out minus ka cos omega t minus kx. Okay. Differentiating previously with respect to time to calculate the Vp. Now differentiating with respect to x. So when you are partially differentiating with respect to time, then x is constant. Partially differentiating with respect to x, then t is constant. Now just divide these two. Vp by del y del x. Vp by del y del x. What it gives? Minus omega by k. Check. Because a cos omega t minus kx will cancel. It is giving minus omega by k. It is giving omega by k. Now in terms of time period, what is omega? 2 pi by t, right? Minus 2 pi by t. And what is this k? K is called wave number, which is equal to 2 pi by lambda, that is wavelength. K is 2 pi by lambda, that is wavelength. Lambda. So if you cancel this 2 pi, it will become minus lambda by t, which is the velocity of the wave that we have already calculated. Which is the velocity of the wave. So Vp by del y del x equal to minus V W. So you can also write the velocity of the wave as omega by k. Omega by k. Not only lambda by t or n lambda. It can be written as omega by k, where omega is the angular frequency and k is the wave number. How many of you don't know that k equal to 2 pi by lambda? Others know k equal to 2 pi by lambda? How it comes? See. The equation of the wave is y equal to x comma t, that is equal to a sine omega t minus kx, or you can as well write kx minus omega t, that is also same. Now If you change x, suppose x is this point, x equal to 5. Then after how much distance x equal to 10 point will come, where the displacement is again same? How much distance it will come? This should be lambda. Because you mentioned that after every lambda distance, the wave repeats its phase of vibration. So if this is at x equal to 5, then when it will be x plus lambda, then it will be repeated. Okay. Now, so can I write this y will be, when we put x plus lambda comma t, then these two will become same. So when x is changed by x plus lambda, then this equation will become a sine omega t minus kx plus lambda. This one. So this is the new displacement. New displacement y, function of x plus lambda comma t, that is equal to a sine omega t minus k into x plus lambda. Now you are claiming that at those 2 points, phase of the vibration or the displacement are same. Means repetition means same. Then we can equate these two. Y of x plus lambda comma t should be equal to y of x plus x comma t. Means after adding a distance lambda, the displacement will remain same. Means whatever be the displacement at x, at a distance x plus lambda, the displacement will remain same. So after lambda distance, this property displacement will repeat. So then it is called wavelength. Okay. Now how to calculate? Just put these functions here. It will become a sine omega t minus kx minus k lambda, that is equal to a sine omega t minus kx. A cancelled. Now from this can I write sine omega t minus kx minus sine omega t minus kx minus k lambda equal to 0. This one minus this one. Then it will be 0. So sine omega t minus kx minus sine omega t minus kx minus k lambda, that should be 0. Okay. Now, if you remember the formula of sine c minus sine d, sine c minus sine d, 2 cos c plus d by 2 into sine c minus d by 2. Sine c minus sine d, write down this formula. Sine c minus sine d, it is 2 cos c plus d by 2 into sine c minus d by 2. I will apply by considering this one as c, this one as d. So first calculate c plus d by 2. What it comes? This is C, this bracketed term is C, this one is D. And don't forget to divide by 2. C plus D by 2. So this one will come 2 cos omega t minus kx minus k lambda by 2 into sin k lambda by 2. That is equal to 0. This one will come. Check. Just write in your copy C plus D and by 2 and C minus D by 2 and check whether these two are coming or not. C is omega t minus kx and D is omega t minus kx minus k lambda. Just calculate C plus D by 2 and C minus D by 2 separately. What is C plus D? C plus D will be 2 omega t minus 2 kx minus k lambda divided by 2. That means omega t minus kx minus k lambda by 2. And C minus D will be omega t minus kx, this part will cancel. It will be plus k lambda by 2 will be k lambda by 2. Okay. Now, this part contains the variable term, that is small t and small x. But see, the second part does not contain any variable term. X and t are not there in the second part. So this product is 0, means this part we can consider to be 0. This part can be considered to be 0 because the variable part cannot be 0. Because if you consider variable term is 0, then there is no wave actually. Because wave is produced due to the combination of x and t, and if you consider this part is entirely 0, then wave will not propagate. There will be no wave at all. So which term can be considered to be 0? This term. This is not containing any variable term. Like x and t are not included here. Then we can write from this that sin k lambda by 2, that is equal to 0. Then what will be the possible value of k lambda by 2? Zero. Any other value is possible or not? Only 0? 1. Angle. K lambda by 2 is the angle. So for which value sin theta will become 0? Only for 0. For sin pi, sin 180 degree, that is 0. Sin 2 pi, that is also 0. Sin 3 pi by 2, 0. Sin 3 pi will be 0. So any integer multiple of pi will be 0 because it is a general solution. Sine 0, then theta equal to 0 means theta equal to n pi. If you consider sine 0 is 0, then if angle theta is pi, then it is 0, 2 pi, 3 pi, 4 pi, 5 pi, all. Even for the negative, minus pi, minus 2 pi, minus 3 pi. For all this, sine function will become 0. You can check from the graph also. This is the graph of the sine function. See, this is angle 0 degree. This one is pi. This one is 2 pi. This one is 3 pi. Check. For all n pi, sine theta should be 0. So in general, we can write k lambda by 2 equal to n pi. K lambda by 2 will be equal to n pi from the general solution. Then at this point there is some displacement. When it is repeated at this point, again it is repeated at here. So this distance at these 2 points, the displacement of the particles are same. So can we say this is wavelength? No, it is twice the wavelength. Then what is the wavelength? Successive repetition, not jumping to another value. There is one value. It is also repetition, but this is not the successive repetition. Successive repetition means then this one. After that, this one. You cannot skip. For getting successive repetition, what should be the value of n? How many gap? 1 gap. So n should be 1 for getting successive repetitive distance. Because if you are getting 2 successive repetitive distance, then it is not the time period. It is 2 lambda then. 2 times of the time period. So for getting successive repetition, you should put n equal to 1. Just put n equal to 1. What you get? K equal to 2 pi by lambda. Because wavelength is defined by the successive repetitive distance, not the repetitive distance here and after so many distance. First repetition and then not the 5th repetition. First repetition, then second repetition. That distance is called the wavelength. Because when you elementary level read the definition of wavelength, it is discussed as the consecutive distance between 2 crests. Consecutive distance, not skipping the one. You cannot skip 2 consecutive. So for after first you have to take the 2, not the 3. 1 and 3, distance between them is not the wavelength. It is twice the wavelength. Okay. So this one will become the calculation of k equal to 2 pi by lambda. After that, we have to discuss one topic, that is the stationary wave formation, and if we complete the stationary wave formation, then you can properly understand what is going in organ pipe and bits phenomena. All are basically based on the Organ pipe is completely based on the stationary wave phenomena. Bits is some kind of superposition. So actually these are the part of the superposition of the wave. So first we will consider the stationary wave, because for the organ pipe we require the concept of stationary wave. Okay. Now, before going to the stationary wave directly, I will discuss the reflection of the wave. If a wave is reflecting, suppose it is going along the positive x direction, now it encounters a wall and reflector and then it is reflected. Then what will be the direction of its propagation? Negative x direction. It is going in the positive x direction, then it is reflected, then in the negative x direction. Then what should be the velocity of the wave? I will put only omega t minus kx will be replaced by omega t plus kx. Is that perfect for all kind of reflection of wave? There are two possible kind of reflection and both are different. See, first one, let us consider this is a rigid rod, and the string is connected. This string is fixed at this point tightly. Means by putting a jerk or anything, you cannot detach the string from this point. Whatever be the jerk I can apply, this point will remain fixed. This will not change. Okay? Now, suppose by applying a jerk at this end, you are producing a wave. I will consider only one bump, and this bump is propagating along this direction. In which direction this wave is propagating? Along the positive x direction. I will not draw the entire wave, then it looks very complicated. Only one, this is propagating. Okay. So what will be its equation? Y equal to a sine omega t minus kx simply, because it is propagating in positive x direction. Now, after some time, if you observe to this wave, it looks like this. Rushing towards the reflector. Then this one. Now what happens? Now it will reach to the reflector. Reflector means this rigid rod. Now the wave reached to the reflector. Now what is the property of this wave? See, whatever be the upcoming points, it will move it up and then it will flow through that point. See, suppose first it will move up point number 1, then upcoming point is say point number 2, then point number 3, point number 4. So whenever the wave passes through upcoming points, it will pull it up and then passes. Now when this wave comes to this point, it will try to pull this point up. But can it do so? Because it is rigidly fixed. It cannot be changed. So what will it do? So this push, due to the tendency of the wave, this will try to pull this point up. But since it is rigidly fixed, it cannot do it. Rather, the junction will apply the reaction force on the string to pull the wave down. It cannot pull it up, but due to reaction of this rigid junction, this will pull the wave down. So the wave immediately changed to this shape. So previously it is a crest. Now the crest is converted to a trough. Or if you consider the longitudinal wave, if it is a compression, then after reflection it will become a rarefaction. So this waves change the phase. Previously it is upward, now it is completely downward. So it is not only changing the velocity, it is also changing the shape. Inverted now. So this is minus. Now this wave is propagating and coming back. Now what is the equation of this reflected wave? A sine omega t plus x. Not only that, additional minus sign should be there. Opposite. Phase is reversed. So previously the displacement is in positive y direction. Now it is in negative y direction. So there is another minus sign in front of it. So it is reversed. Okay. Now this minus sign can be written like this. Plus pi. Without taking this minus sign outside, I can take a plus pi inside. Why? Because this can be splitted into parts, that sine omega t plus kx into cos pi plus cos omega t plus kx into sine pi. Sine pi will be 0, so next part will be 0 and cos pi will be minus 1. There is this minus sign. So phase is not only, phase is changed by a factor of pi. Pi phase difference means opposite phase. Because we are discussing the sinusoidal function. Check. This point and this point are in opposite phase. What is the angle between, difference between them? Pi. This one is pi by 2. This one is pi. This one is 3 pi by 2. So difference between them will be 3 pi by 2 minus pi by 2. That is pi. And if it is difference of 2 pi, then it will be in the same phase. This 2 point. Same phase. If there is a difference of pi, then opposite phase. Same phase means phase difference, angle difference is 2 pi. Opposite phase means angle difference is pi. Since we are considering sine function, adding pi, initially one minus sign will come, because to remind you that the opposite phase will occur. Previously this one, now this one. Okay. So this one, write down, this is the reflection of a wave from a rigid boundary. This one is the rigid boundary, this junction. That's why it is called reflection of a wave from rigid boundary. And both type of wave will follow this rule, not only the transverse wave, transverse, longitudinal, both. Reflection of wave from rigid boundary. So wherever there is a reflection from rigid boundary, not only the direction of velocity will change, the phase of the wave will also change by a factor of pi. Now, there is another type of reflection that is from a movable boundary. See, this is the rigid rod again. This is the where you produce a one bump. This is some kind of ring which is actually encircling this rod. Okay, and this ring can move without any friction through this axle. Rod is behaving like an axle and this ring can move up and down. Now when you produce this bump, this will again move in this direction and its equation is similar to this one. Then this wave moves forward, and it will reach to this point. But now this portion is not rigidly bound, so the wave can pull this portion up. Previously it is rigidly bound, so it cannot pull. Rather, due to reaction, it will be inverted. Now it can pull it up. So the reflected wave will be like this. Reflected, reflected, now again. So now they are going, now they are coming back. Now what happens? Is there any change in shape? Shape is not inverted. Crest is reflected as crest. Compression will be reflected as compression, not changed. But only the velocity direction will change. So this wave, reflected wave, has an equation A sin omega t plus kx only. There is no additional minus sign in front. So phase will remain same, only the direction of velocity will change. So this is called the reflection from a movable boundary. Reflection from a movable boundary. Okay. Now let us consider this pipe, and this side is closed. Inside the pipe there is air, and if you are putting a vibrating tuning fork, then a wave will generate in the air column and wave will travel through the air column. Vibrating tuning fork is held here, then through this air column a vibration will propagate. The vibration will come to this point and then reflect from this point. Now the air particle which is in contact with this surface, this is a solid surface, so this air particle is suffering huge friction, so it will not move from this portion. And when the wave will come here, can it move this particle from this point? No. So in this case it is reflected from the rigid boundary. That is the case of closed organ pipe. Now if the both end of the organ pipe is open, It is the vibrating tuning fork. The wave will come to this last air particle. Now it can move the this particle because there is no other solid surface. So it is open surface, free or exposed to air. And where the pressure is more, for the static air pressure will be more. So outside the pressure is much less. So this air particle can move freely. So the wave will reflect again. But now the reflection is obeying this rule. Reflection from movable boundary. Reflection from movable boundary. Don't think that after coming to this point, sound wave will go outside. It will reflect again. Both from this it will reflect. From this it will also reflect. Don't think since it is open it is coming out completely. Why? Because sound reflects if there is a change in pressure, because it is mechanical wave. So in which direction medium is more dense, the sound will reflect in that direction. It will come and then reflect again, following the rules of this one, movable boundary. So don't think that sound completely comes outside. So rigid boundary means high pressure, movable boundary means low pressure. So from both ends sound can reflect, since it is longitudinal and mechanical wave. But from rigid boundary, when it reflects, there is a phase change, and from movable boundary, when it reflects, there is no phase change, only the direction change. Now based on this reflection, we have to study the stationary wave and the organ pipe problem. Once we complete the stationary wave, organ pipe problem will automatically be solved. And then one more topic, that is beats.